This video is about solving differential equations using Mathcad. So we know that the command OD solve in Mathcad gives us a numerical solution, but it doesn't give us an analytical solution. But we can find an analytical solution using Laplace transformation. So first I will do an example with and use the command OD solve. So shift here, shift slash gives me dy dt, so like that, and this is t here. So this is just a first order differential equation times y t, and control equals to, which is the equals to, and this is the differential equation, and the initial condition, let's say y0 is 1. So I want to solve this one using ODE solve. So ODE SOLVE, it will have two arguments. The first one is t, which is the independent variable, and second one is the range of the independent variable, so being the 0 being the first value. So let's say the range is 50. So the solution is so since I have started a block, a solve block, I forgot to give the command given, which is essential for a solve block. So I am doing that now, given, and now it's done. So when I solve an ODE solve, when I want to use the command ODE solve to solve a differential equation, I have to use a solve block, and solve block begins with the command given. So now I will plot this one, insert graph xy plot. So that is t here and yt here. So I have the solution there. So this is using ODE solve. Now if I want to find the numerical solution, I will use the same differential equation, so but I will use a different variable, dependent variable. So let's say that's p. So this is t here, and then plus 6 times p t and 0. That's the differential equation. Now I want to solve this one. Here this is gone for the time being, so because it's probably taking for another differential equation, so I will bring this lower. Okay, so the initial condition is still the same. P0 is 1, because it's the same differential equation. I'm trying to do the same one, but I will try to find the analytical solution. So what I will do, I will convert this one into Laplace transformation. So this is the equation here. I'm writing it again, but without just the left hand side, basically 6 times p t, and then I will use Laplace. I will use the symbolic window here. It's from, I can find it from toolbar, the symbolic toolbar I'm using, and I can find Laplace here and for t. So that's the Laplace transformation for this. So basically this is the Laplace transformation of dp over dt plus 6 dp. So let's define something called ls. So this is the Laplace. I will try to write the right hand side. So s here times l. So that's the first term here, s times l, minus p0. Minus p0 is 1, so I will just write minus 1. So I will have to write it manually, and then plus 6 times that one is l. This is just the Laplace transformation. So the Laplace transformation I'm writing in terms of l. Now this one equals to 0, control 0, and I will solve it for l. So I will again use the solve command from the symbolic toolbar. Sorry, not factor. So mistake, it should be solved. So basically that's solve for L, and this means nothing here. Okay, so that's the solution. So this one is the Laplace transformation this is the solution for L. Now if I do the inverse Laplace transformation of this one, I will just get my yt. So this is L, the Laplace transformation of the solution, basically this one. So if I find the inverse Laplace transformation, if I do the inverse Laplace transformation, I will get the solution of the differential equation. So that's what I will do now. So yt will be, let's define this one again, is just Ls and inverse Laplace transformation. So inverse Laplace is again in symbolic toolbar, inverse Laplace, and this one will be for S, and I have the solution here. So since I have the solution here, I can do this one, I can plot this one. I'm running out of space here, so yeah, what I will do, I will just use a smaller view. I will zoom it out a little bit so that I can just have a look here. So yeah, so now I will xy plot here. So that's t here, and then I have yt and pt. Oh, that's yt basically, sorry, that should be pt, should have been. So yeah, there it is, sorry. So because I wrote yt here by mistake, that should have been pt. So here in the y-axis, x-axis, I'm changing the range, so making it 0, and then maybe here making it, I don't know, maybe 5 or something, or 4. Yeah, and you can see they are overlapping. So basically this is the same solution. This is the analytical solution, and this one here was just the numerical one. So yeah. So it's a new window here. I want to do another problem for a second order differential equation. This is an arbitrary differential equation. It doesn't mean anything physically. I have just done it. So these are the two initial conditions here, and I want to solve it analytically using Laplace transformation. So for what first I will do, as before, I will find the Laplace transformation of this one. So the second order differential can be found using keyboard shortcut, which is Control Shift and slash. Also it is available in the calculator toolbar here. So sorry, that's lowercase t, and that's 2 here, that's 2, and then plus 6 times shift slash gives me the first order one, and this is t here, minus 5yt, 5 times y t. So I want to find the Laplace transformation of this one. So I will go to the symbolic toolbar here, and I will use Laplace. So that's for t, and this is the Laplace transformation. So I have here 1, 2, 3, 4, 5, 6 terms. The first one is, so basically this one, the second one and the third one, these two are the initial conditions, and I have to write them manually when I write them. So I will define Ls as the Laplace transform version of the differential equation. So S, the first term is S times L, so that's S square L, S square times L. Then the second one is minus y0, so my y0, the initial condition y0 is 1, so minus 1. The third term is basically dy0 over dt, or y prime 0 basically. So that's also 1 here. So minus 1 again. The fourth term is 6SL and plus 6 times S times L. Then fifth term is 6 times Y0. Y0 is 1, so 6 times 1 is 1 minus, so it will be minus 6. And the last one, which is here, that is 5 times Laplace, so 5 times L, so minus 5 times L, minus 5 times L. So this one equals to 0, so control equals to 0, and I want to solve this one for L. So I will go to the symbolic toolbar, I will use solve here, and then I will do it for L, and I will get the Laplace solution here. This is the solution of the differential equation in terms of Laplace. It is a Laplace transformed version of the solution basically. So I want the time domain solution because I wanted to find the solution of the differential equation which is in time domain. So what I need to do is I need to find the inverse Laplace transformation of this one. If I can find that, I will get the time domain solution. So I will do that. Yt here, that is equals to Ls and inverse Laplace transformation of that. So I will go again to the symbolic toolbar. I have the inverse Laplace transformation command here, that one, and for L, and I will get the, for S, and I have the solution there. So this is the solution. This one is the solution of the differential equation. So I have sine hyperbolic and exponential term here, and that's the solution of the differential equation as I